And then, as you know, we have uh, a Discord channel. That's where you can discuss about anything. Try not to discuss politics, simply because it's not a good idea. Uh, I try to avoid politics because, let's say, if you start a business, if I start a business, if I bring politics, I will lose 50% of my customers. I'm not in the Discord channel, so don't ask questions to me on Discord because I will not be able to respond. Second, it's a good place for you. In the first lecture, I think I gave this analogy, and I'm not trying to make fun of you, or if you know anyone who were in prison. Some students literally think that this class is like a prison. So if you are in jail, if you don't like with your living like quality of life in jail, if you just gossip with your cellmates, that thing will not change anything. So if you just keep the discussion in Discord, like keep the complaints in Discord, it will not change the quality of the class. One of you need to talk to me, and I will really appreciate that. So I actually learned this material when I was in high school. I was part of a national team, like physics Olympiad team. I went to Canada, Turkey, represent Indonesia. So it has been, my point is, it has been 30 years. And F is still equal to MA. Coulomb's law is equal to K times Q1, Q2 divided by R squared. The only thing that is different is your questions. Okay. Your perusal comments, especially if you say, add result, Hariadi, then I will get an email. Those are the different things, and that will, I cherish that. And that makes this teaching more fun. So Discord channel. Next is I'm gonna go through two convention in math. Any questions so far while I look for the, oh, exam 2. When is your organic chemistry exam 2? Do you know? Huh? 28. So if you can, so I'll check whether your exam 2 is also in 28. If that's the case, then you have the option to postpone it by one lecture. If that's your, that's up to you. So instead of exam on Friday, it will be on Monday again. So, okay. So first, we will talk about right-hand rules, and there are two versions of right-hand rules. But in some problems, you're asked whether it points plus x plus y or minus x minus y minus z. So we know that x and y, they are perpendicular with respect to each other. But what is the direction of plus z? So the direction of plus z, is it A or B? Which one is plus? To do that, what you need to do is you use right-hand rule. So you need to make this curling motion, and then that will point the z-axis, the positive z. So like so plus and minus. Similarly, one can change the question. So let's say this is x, this is plus y, and you know that this is minus y, of course. Where is plus z? Because if it points down, it's also perpendicular with respect to plus x and plus y. What you need to do is you need to make a curling motion from x and y, and then it will point to plus z. Okay. So this is not plus z, this is minus z. Any question? Okay, good. Easy. And next, I will add one more slide to your cheat sheet for your exam, which is we discussed this on Wednesday, and I think Fabian and one student on the left wing of the class asked me about this. Yeah. So basically, you start from X because in life X is before Y. So we start with X, Y, and then Z is plus Z is up, minus Z is the opposite. So yeah, it can be something like this. So what is plus Z? Is it points towards you or towards the whiteboard? So, and we will discuss what this means. Good question. Any other question? Okay, so back to the slide right now, which is the power of a battery. So to avoid a sign mistake, I will add this picture on the exam. So basically, if the current goes from minus electrode to plus electrode in a battery, then the power is plus. If it's the opposite, like if when you charge your cell phone, the sign of the power is negative. So, and then next I probably spent too much time discussing about William Gilbert. Yesterday I went to a seminar, and trust me, this is going to be a far shorter story. Yesterday I went to a physics seminar, and we learned about Helmholtz. So many chemists are in the room. Helmholtz, probably you have encountered Helmholtz free energy. Basically, I think it's the energy, free energy at constant temperature and volume. Turns out that he is also a physician and a physicist. So there are many examples of those people. So you can do this. All right, so the iClicker question is basically, another way of saying this is whether magnetic monopole exists. So what is the answer? The answer is it doesn't exist. So if you read Perusal, you will know, and we will discuss it in this lecture. And then we finished the lecture by discussing about, I presented a string of facts or observations that people have done in many centuries, and those observation cannot be explained by Coulomb's law. So I will probably start with the closest one. This is just a simple demonstration. The wire is not charged, but what I'm gonna do is I'm gonna flow currents, and you need to pay attention to this position of the wire. Okay. Let's see if I can zoom it further. So I'm gonna flow a current, and then unfortunately this is not labeled, but when I flip the switch, pay attention to this part of the wire. Did you see that? So they get attracted. And then for this one, I know that the current are pointing towards the same direction. And if I flip, if the current point toward the opposite direction, what do you expect? Just guess. They repel each other. So this type of things, people quickly realized that our understanding was not complete. So that led people to develop the theory of magnetism. Okay. Next is we have a demo. You know what this thing is? Have you seen this? What is this thing? So when I was an undergrad, this is how I learned. We didn't have Perusal. Going on here. Power cable. Anyway, perhaps it's time to give up. Okay. Oh, all right. So maybe the demo is for next class. But some of the demo is very simple. You know, we have, and you have seen it. So let's say we have two bar magnets, and we put north pole, like the same poles close to each other. What you get is you get repulsion between two bar magnets. You know this. And then the colors, I don't know what blue represents, what red represents. I think blue represents north. I don't remember exactly. But basically, if both of them are north pole, then we get the field will look like that. The field points away from the north pole. So if we have a bar magnet, that's actually the demo. The field points away from the north pole, and it will point towards the south pole. It looks just like that. So the iClicker question says, what happens if we break this magnet into two? So we call this magnetic dipole. It's analogous to positive charge and negative charge. So this is the electrical field analog of the magnetic dipole. So plus charge, the field also goes like this. The question, the iClicker question, which has been described in your proposal, does magnetic monopole or the analog of single charge, either positive or negative, exist? So you may think that if you keep on splitting magnets into smaller and smaller magnets, at some point you will find a magnetic monopole, meaning an object that only has either south or north pole. Turns out that other than one occasion, we have never seen magnetic monopole. It doesn't mean that it doesn't exist, right? Proving something that doesn't exist is very difficult. And we encounter that, for example, in the election. I know that I shouldn't talk about politics, but this is probably the only time. So proving that there is no election, what do you call it? Something that is not right. Yeah, fraud. Then it's difficult. Similarly, proving that magnetic monopole doesn't exist is very difficult. Meaning it's hard, especially if because the theories say that a magnetic monopole existed during Big Bang, and it has been observed once, but we cannot observe that thing again. Either that paper is problematic, or scientific fraud, or it was just very difficult to expand. Back to magnetic monopole, it doesn't exist. So maybe on the exam, this is just one example. I say like which one that doesn't exist. Okay, so I may say this one doesn't exist, by the way. This is a magnet, so this is which one exists. Let's see. This one, okay, north and south. Okay, so you know that this one existed, and maybe option B, south, north, and I'm gonna put the label big so I don't trick you. We don't do a trick question here. Then B doesn't exist. And then I may write south. Wow. So does this thing exist, this magnetic material? This is a representation. If there is any magnetic monopole, it would look something like positive or negative charge. So I'm not gonna say, I may not use the word monopole, but you should have some cartoon picture in your head what monopole would look like. Okay. We have covered this opposite pole attract and like poles repel, so that thing is pretty straightforward. And this is the demonstration that we did, which is if we flow without currents. So without current, basically the net motion of charges is zero. So the charges, they don't move. They fluctuate, but they don't move. There is no forces. But when we flow current, when we force those charges to move, then there is, the name is Lorentz force. So I think Holden answered my question last time. So the reason why there is force, because charges move. Any question? So this is just introduction to magnetism. I mentioned about Lorentz. Lorentz is a physicist. He's famous for many things. And somehow we honor him by naming the force that is in the box after his name. So we call this force Lorentz force. He didn't develop it, but we honor him. Similarly, last time I mentioned that Ohm's law actually was derived by Ohm, but the one that read his photo handwriting was Wheatstone. And Wheatstone has high ethics and called that law Ohm's law. Either he was shy or he has high ethics, most likely both. So Lorentz force. So if the charge don't move, and force is a vector, then the force is only due to the electrostatic attraction or repulsion. So this is equal to the charge and the electric field. But when the charge moves, there is magnetic field. Okay, and the symbol for magnetic field is H or B. H for Hariadi. So actually, the symbol is H or B. But in this class, we use B. But H, some books use H. And this is something that you shouldn't do, by the way. But we are stuck with this symbol. When I was in grad school, my lab mate labeled all of his strands like A, B, C. And then he placed another order, A, B, C. And then placed another order for a different project, strand A, strand B, like strand means DNA strand. And soon he will be confused. So B is due to the physics notes of a famous scientist. So because the first vector was A and then B and C. So we stuck with B. B is for magnetic field. So the force, and this is a law, something that you cannot derive. This is based on measurement. V, B, and then there is sine theta. What's sine phi? And then, so you ask me, this is a vector. V is also a vector, but we will only care about the magnitude. V is also a vector. Where is the distance? Where is the direction? At what direction this VB points to? Sorry, it wasn't a statement. I'm just pretending that I was asking that question. So the direction is, let's come up with a symbol. Your book doesn't use that symbol. Let's use, I don't know, physics one. Maybe R, not for result, but it's just R. So this one is for right-hand rules. You get this direction by right-hand rule. And the magnitude of right-hand rule is equal to, sorry, the magnitude of a unit vector is equal to 1. Has anyone ever learned about right-hand rule? The right-hand rule? How many of you have learned the right-hand rule? How many of you have read Pruzel? All of you. Okay. Maybe I forget to assign that section to you. So it turns out that the direction of the force you can determine by the right-hand rule, and is perpendicular with respect to V and B. So it's perpendicular, and this is based on experimental measurement. So one thing, like the next slide says that mention about the work. We know that work is the displacement times force. Okay. And because they are perpendicular with respect to each other, so the force is perpendicular to V, then the work is, so work is equal to F times delta X, right? And there is cosine theta. Let's just call it phi. We have used phi, so let's use theta. And delta X, you can calculate delta X as V times delta T. So V is a vector, F is a vector. So if F and V are perpendicular, then theta is equal to theta is equal to, if they are perpendicular, theta is equal to 90 degrees. So cosine theta is equal to 0. So there is no work. So you may ask me, like, why do you ask me to study magnetic force if they don't do work, right? Because electrostatic interactions, you can accelerate charges. It seems more useful. Why do we spend a lot of time? Why we will spend a lot of time studying magnetism if it doesn't do any work? Any guess? How about you? Yes, you. 3 people, four people like that. Yeah, you with glasses, with cool glasses. Yeah. Okay. Oh, okay. So it turns out that magnetic field is really useful. Let's say you fantasize to own a cyber truck. The reason why electric cars are more efficient is because of magnetic field. And you will see that the movement will be generated with very little friction. If you are in biological science or biotechnology, we use mass spec a lot, and that thing relies on rotary motion due to magnetic field, which we will learn very soon. So the question is, how can we get a vector from two vectors? And this is not a night clicker. The answer is right-hand rule. Before we study right-hand rules, and we will do a lot of iClicker, don't worry. A little bit about the magnetic field, or B. The unit is Tesla or Gauss. One Tesla is very strong. Typical NMR machine is on the order of Tesla. And typically when you go to that room, you have to leave your gadgets because it's dangerous. Your gadget may just fly to the machine. If you have to take, let's say, an MRI imaging, last year when I was teaching this class, I had skateboard accident, and I had to do MRI, which is very boring because it takes a long time. But basically, it's true. It's not just a gossip that when you are in that MRI room, you have to leave your device outside the room. Okay, so let's finish the symbols. So we have X, so X, Y, and initially I drew like this because let's say the point of view is from this angle. But if you view this plot from using front view, then it will look like this, X and Y. In math, there is a way to represent Z from front view. So if it points towards you, then you make this solid circle and an open circle. And then if it points away from you, this is actually true if you use right hand rule, Y, X. So Y, X plus Z, that means points away from you towards the whiteboard, it looks like that, X. And you don't need to memorize this as long as you know the why mathematicians choose this symbol. It is actually from arrow. So if you do archery, if the arrow looks like this, then you're good. That means you will stay alive. But if you see arrow looks like this, then you need to run. That means the arrow points towards you. So are you ready for a right-hand rule? So right-hand rule, there are two versions, and you're welcome to use both of them. Okay, so basically, right-hand rule means you have to use your right hand, and I only use my right hand. Some people use right hand for positive charge and left hand for negative charge. You can do that, but I just use my right hand, and if I know that the problem asks for negative charge or electron, then whatever the direction of F that I find, I just choose the opposite. Let's say plus X, I find plus X using my right hand rule, but the particle is an electron, I answer minus X. So you guys haven't learned this before? So how do you do perusal? I'm just curious. Like to try to game the system, which is still good. Even if you game the system, it's better than if you don't open the textbook. So I still consider a big win. So the first one is I think I will be in trouble because this one maybe I should have practiced this. No, okay. It doesn't work. It doesn't work. So just maybe I should point like, so this is my right hand, of course, and the direction of the thumb is the direction of the force. The direction of your pointing finger, I think this is index finger, is the direction of speed, and the direction of your middle finger is the direction of the magnetic field. So like this. So force, velocity, and when I say speed, it's velocity, not speed, and magnetic field. So that's one. If you Google or if you read Mastering Physics, they have a different right hand rules. This is the direction of the speed, my thumb, and then the direction of the field is the whole palm of my hand, so like this, and then the direction of the field is like that. So you have to make a curling motion, and that's the direction of the field. So which one is easier? Doesn't matter. I like it, this thing. You know why? Because after I left my band, I was a rapper. This is what rappers do, right? Because they compute Lorentz force. Okay. So we will have a lot of practice. Let's practice with the first problem. This one, if you know physics, if you know math, you don't need right hand rule. Okay. The formula is, and right, for this practice problems for today, the angle phi is 90 degree. And sine 90 degree is equal to 1. So for this I-clicker problem, F is equal to Q times V times B. And then this one is right hand rule. So the first one shouldn't take you a lot of math. The speed is 0. So what is the force? The field is uniform, goes from left to right. The charge is positive. Ten more seconds. 5, 3, 2, 1. Okay, good. So the answer is A. Because V is 0, then F is equal to 0. So next is non-zero. So in the next few, and I apologize, there should be not here. So I'll fix it before I upload this lecture notes this afternoon. So in this problem, you will need to use right-hand rule, and it's actually drawn here. Okay. So calculate the magnetic force on the positive charge. The charge is positive, it moves to the right, and the field also points to the right. Sorry, I apologize. In this case, sine is actually 0, not 90 degrees. So in this case, you need sine theta only for this problem. And sine 0 is equal to 0, and sine 90 degrees is equal to 1. Let's spend 30 seconds. And you can do it with your neighbor. All right, so 10 more seconds. All right, so basically all of you have answered. So what is the phi here? I apologize, maybe I wasn't being clear. So phi is the angle between V and B. So everyone get a full credit. Phi, I apologize, phi is the angle between V and B. And B is horizontal, V, the velocity is also horizontal. So what is the angle? 0. So sine phi is equal to 0, so F is equal to 0. But after this problem, for sure, phi is equal to 90 degrees, okay? Trust me. All right, see? Now the particle, the positive charge, is moving downward. So negative y, and the field goes along positive x-axis. So what is the magnetic force? 15 more seconds. If you're not sure, just pick a random option and we will take time after this iClicker question. Okay, so so half of the class says D. Okay, so V is the V is the index finger, so V points down, and then and then B points right, and then so F is my thumb. Right? So V points down, B points to the right, which is your left, but I'm just staring at the figure here. So so V, so sorry. So should be minus Z, is that right? Ah, I see. Okay. No. So this is correct actually. It's point. Okay. So the axis is X, Y, and then this one points towards you, right? So it points. Sorry. I need to stare my computer. So it points towards me. That means it's plus Z. Okay. Let's use the other right hand rule, which is V, and then it points like that. Okay, so V points down, the field points to the right. Sorry. Is this clear or confusing? Because maybe I need to do this, okay? Yeah. So V points down, V points this direction, and then the direction of V is like this, okay? Which is positive Z, okay? And let's use our favorite right-hand rule. So V points down, V points down, my index finger, B points to this way, and the force points towards you. Okay. I'm right now, the computer screen face the same way as your cell phone or computer screen. So the answer is, okay. Is that clear? If it's not clear, then like anything else, you need practice, and then it will be straightforward. Okay. Now it's negative charge. Okay. And then the field points away from you. So it's negative charge points to the right, and the field points away from you. Yeah. All right, 30 more seconds. All right, so basically almost all of you already answered. 5 more seconds. what is the answer? So so the particle, so index finger is speed, so move this way, and then the field points into the screen or into your computer screen. So the force for positive charge points up because the question says that the charge is negative, so you need to flip it. So magnetic force is in negative y direction. So the answer is, yeah. Where what? Oh, x. Oh, yeah, x. Say x basically. If you look at a moving arrow, x is moving away from you. If you shoot an arrow, and then if you see points, then it's the arrow is moving towards you. Okay. So basically, this is the one out of 4 or 5 right-hand rules that will be part of exam 2. So the reason why only a quarter of the screen is shown because there are 3 other right-hand rules. And then like anything else, the second time you see right-hand rules, the easier you will find to master the concept. Okay. Since already opened this. Okay, so basically, turns out that, and we will, so on Monday, we will talk about mass spectrometry, which is a very powerful technique. What mass spectrometry does, it change particle with non-zero charge per mass, and then change the trajectory into circular motion. And in circular motion, the speed is the same, but the direction changes or the velocity changes. Since the speed is the same, so the kinetic energy also stays the same. Right? Kinetic energy is 1/2 mv squared. So we will have one more iClicker question. And this one is, I need to show the video. So some of you asked me whether there are additional resources for problems. You can go to your mastering physics and study area, and there are practice quizzes, for example. But what I will show you right now is video for the video from mastering physics. So give me a second. Oh, this one. So this is the video. Volume. Here to here. I also have. So what I'm. So I promise that this class is very useful. That's a promise. So let's say you try to figure out the direction of magnetic electron in the presence of magnetic field, then you can use the knowledge that you learned in this class. In this demonstration, I have a tube connected to this power supply. When I turn on the power supply, you get a nice beam of electrons flowing from here to here. I also have a magnet, South Pole, North Pole, and what I'm going to do is I'm going to bring the South Pole up towards this end of the tube. Now the question is, which way will the beam deflect? Will the beam deflect up? Will the beam deflect down? Will it deflect towards me? Will it deflect away from me? Or will it not deflect in any way? Okay, so in physics, it's always good to draw. So basically, you have a cathode tube ray, or CRT. Again, no politics in this class. Wait, cathode ray tube. Sorry, cathode ray, which is the core technology of old style TV. So basically, you have a electron gun, and then electron move in his experiment is moved to the right. Remember, and then he put south pole close to the electron, the path of the electron. The question is whether the electron move down, up, towards you, or away from you, or doesn't move at all. So again, negative charge, field, based on what we learned, there should be magnetic force. Okay, so the south pole, that means the field points towards the south pole. So if you bring south pole nearby like this, then the field points towards the south pole. Okay. So basically B, V vector, and then if there is a force, and then the charge is negative. Very good. You need to use right-hand rules. This is the last problem in the class. Okay, so almost all of you have answered the iClicker question. It seems pretty easy for many of you. So we can continue the video. Are we good? And you have in your lecture notes, you can click the video link. So let's finish this video. I don't know why it's not moving. Because I haven't clicked the play button. Did you see that? The electron moves up.
So bringing the south pole in this way caused the beam to deflect up. How can we check to see if this is correct? We need to use the right-hand rule. So if my thumb is the direction of the current of the flow of electrons this way, and the magnetic field is pointing away from me, if I curl my fingers, it says that the beam should go down. But that's not correct. Why? Because the beam is charged negatively, so we need to put a minus sign in front of that direction, so it actually it turns up.
All right, so any questions? All right, have a nice weekend. I'll see you on Monday.